Science is a body of knowledge. It's been grown and developed and changed over a period of thousands of years, but it's a concerted human effort to understand, or at least to understand better, the history of the natural world and how the natural world works. We use physical, observable evidence as the basis of that understanding. We use observation and experimentation to ask questions. Science is basically just asking questions and actively seeking to answer them. There are overall two major types of science. There's discovery science based on the observations of the natural world, and hypothesis-based science based off of experimentation. An ecologist observing the territorial behavior of bluebirds, or a geologist examining the distribution of fossils in an outcrop, are trying to find patterns in natural phenomena. They just are observing the natural world and gathering data, which could be qualitative or quantitative. But say a chemist in the lab observing one chemical reaction at a variety of temperatures, or a nuclear physicist recording the results of bombardments by neutrons to a particular type of matter, are doing experiments to see what patterns emerge. But the critical commonality for both of these is that everyone who's doing them are making and recording observations of nature, or at least of simulations of nature, in order to learn more about how nature, in the broadest sense, works. This is the first time you've seen a green star in one of these videos, and when you see that, that means there is either an image or a diagram that I expect you to copy into your notes. However, in this case, you only need the larger text, not the sub-questions under each. So the scientific method is a useful organizational method that started out as a list of things scientists do in a paper from 1945 and evolved from there. But it's an ongoing process, so I prefer this circular presentation over the linear presentation you may have had before. Human beings are naturally inquisitive, so we observe the things around us and we often come up with questions about what we see, and that leads us to develop hypotheses. Once you have an hypothesis, you can test that hypothesis using an experiment or further observations, and then once you have the data, you can analyze that hypothesis and either accept it or refute it or change it. Results of a scientific study are often presented in the format of the method, even if the research was not conducted in that fashion. Science can be and is done this way, but it doesn't have to be. At its most basic level, what scientists do is make models. A model is any simplification, substitute, or stand-in for what you're actually studying or trying to predict. They're used because they're convenient substitutes, the way that a recipe is a convenient aid in cooking. So the ingredients list on a bottle of ketchup is a model for its contents. So it's similar to what it represents. So the ingredient list is a fairly accurate guide to the contents of the ketchup. So models are ubiquitous. Nearly everything we encounter is a model in science. But to develop a model, you analyze a complex situation, you disregard the irrelevant factors, and you create something that describes the essence of a system. It could be a diagram, it could be a picture, it could be a mathematical formula. Models are widely varied. Example, the model of an atom below, you had the Dalton model of the atom, then you had the Bohr model, and now you have the electron cloud model. So as we learn more about the atom, the model is refined, coming closer to reality. So it allows you to disregard complex, irrelevant factors to give you predictive power over how something will work. It all comes down to what is a system. Well, a system is a set of particles or interacting components considered to be a distinct physical entity for the purpose of study. So essentially, a single object and the items that immediately affect it are a system, and you're going to make a model of that system to understand it. Now we come to one of the most common misconceptions, and it really is just that people use the word theory and hypothesis as if they were interchangeable, but they're really not. When you say that evolution is just a theory, that's just a completely ignorant statement. So a hypothesis is a conjecture based on knowledge obtained while formulating the question. It's an untested explanation for how. Typically, you see it as an if-then in beginning science classes, and it must be testable and it must be falsifiable. If you cannot prove it wrong, it's not a valid hypothesis. A theory is not how, a theory is why. So it's a comprehensive explanation of some aspect of nature that is supported by a vast body of evidence. Many scientific theories are so well established that no new evidence is likely to alter them substantially. No new evidence will demonstrate that the Earth does not orbit around the sun, which is the heliocentric theory, or that living things are not made of cells in the cell theory. I think you get the idea. Scientific knowledge is closely tied to empirical findings and can remain subject to falsification if new experimental observations incompatible with it is found. No theory can ever be considered final, since new problematic evidence may be discovered, and so a new theory may be proposed, you may modify an old theory, what have you. But a law is different from these. A law is what happens. They don't posit a mechanism or an explanation. They are merely distillations of the results of repeated experiments. So the law of universal gravitation is different from the theory of gravity. So laws are what happens. They're usually a math formula. They can be proven wrong, but it doesn't happen very often. The scientific method uses objective experimentation to predict, verify, or refute an assertion made by a theory. Based on the results of the experiment or experiments, the theory is modified. The process involved with prediction, observation, and verification or refuting are repeated, continually tested, and modified until the theory fits all possible experimental observations. There's some basics of graphing you need to remember in this course. The first is one I'm sure you've heard before. The dependent variable is your responding variable, and it is found on the y-axis of your graph. The manipulated variable is the independent variable, and it is found on the x-axis of your graph. Now, which type of graph you use in a given situation is determined by the type of data that you are collecting. Bar and line graphs can seem nearly interchangeable, but generally line graphs work best for continuous data, whereas bar and column graphs work best for categorical data. There are exceptions to every rule, but some broad rules of thumb there. Line graphs do not have to be change over time. What they have to be is continuous data, quantitative data, where you cannot count the number of different values. Sales, height, profit. Pie graphs are handy for percentage data, but we will not see them very often. Now, one mnemonic you may not have seen before is Sultan. When you are making a graph, you need to follow the rules of Sultan. Your scale should be consistent. 5s, 10s, 20s, don't change it in the middle. It should fill the area that I provide. If I give you a half of a page to make a graph, you should use the whole half of the page, not just one small piece of it. Your units should be labeled on both axes. You should tell me how your data was measured. And they should have labels. What is being measured? If you don't have units and labels, your graph is meaningless. All graphs should have a title, and typically that title should incorporate both the independent and the dependent variable. As far as accuracy and neatness, basically computer generated is best. If you need help making Excel graphs or some other digital graph, please let me know. Hopefully this slide has entirely reviewed the basics of an experiment. As we go forward, I need to make sure you know what these words mean. The independent variable is the variable that you are changing. The dependent variable is the one that changes because of what you did. If you change the amount of fertilizer that a plant is receiving, the dependent variable is going to be the amount of growth that the plant did. Your constants are your controlled variables. You keep them the same for all the tests. So in our plant examples, same temperature, same water, same type of fertilizer, same type of plant. You get the idea. A control is different from a controlled variable. A control is your source for comparison. It is your baseline. It is how you know what you did actually made a difference. Now, besides control, there are also trials. And the purpose of trials is to ensure accuracy. User human error is common. If you do the experiment multiple times and you always get the same result, you will avoid that error and ensure the accuracy of your experiment. A few more points that I need to make sure you are aware of. The first is one I'm sure you've heard before. Correlation is not equal to causation. Correlation is when two or more things or events tend to occur at about the same time and might be associated with each other, but aren't necessarily connected by a cause-effect relationship. For example, in sick people, a runny nose and a sore throat correlate to each other. They tend to show up in the same patients. That doesn't mean that runny noses cause sore throats or that sore throats cause runny noses. Forgetting that leads to sloppy thinking. The point to all this is that if you are writing an argument and you claim a cause-effect relationship exists, you should double-check it, triple-check it. Make sure that it is causation and not mere correlation. It's hard to nail down causation conclusively, as evidenced by tobacco company lawyers who argued for 40 years that smoking merely correlated to lung cancer rather than actually causing it. The least you can do is pause and ask yourself what other possible causes exist in addition to the one you point to in the paper. If they do exist, you need to think through the evidence and determine why these other causes are less likely than the one you propose. Another point is that a hypothesis can never be proven to be true. I know we kind of addressed this earlier. A hypothesis can be refuted, it can be falsified, but it can never be proven. It can only be supported. However, if a hypothesis is tested again and again and is never falsified, it may become elevated to the level of a theory. And one last thing is the difference between probability and statistics. Probability deals with predicting the likelihood of future events, while statistics involves the analysis of the frequency of past events. Really, what I'm looking at here is that probability uses deductive reasoning. We hold a theory, and based on it, we make a prediction of its consequences. That is, we predict what the observation should be if the theory were correct. We go from the general, the theory, to the specific, the observations. Statistics is different. Statistics goes in the other direction. We go from the specific to the general. You make many observations, you discern a pattern, you make generalizations, and you infer an explanation of or a theory. That's inductive reasoning. So basically, probability is going to be you have a model, predict the data, whereas statistics are you have the data, predict the model.